in the simulation of wind turbines, there are people working in the atmospheric model. We are working together with people from some tech in the wind structure interaction, and from several points of view. What I am showing here is the detailed modeling using computational fluid dynamics software to simulate the flow around the wind turbine. There are also some people working in flow and acoustics. Another people are working in the material failure model. And all these work packages are integrated. That is, the idea is to connect all of them and make a kind of joint system simulation, a very large system simulation of this system. And finally, I was surprised by the talk given by Marco yesterday. There are people working also in the aspect of public acceptance of these kind of machines, and these people are psychologists, and they work and try to see how to design these devices to be accepted by the public. So the link here is a link to the project, and you will find there some more information. So the wind turbine can be described as a mechanism, and from the point of view, it is a flexible mechanism which is submitted to dynamics efforts. So we can model it in the context of flexible multibody dynamics. And what we look in flexible multibody dynamics is to the dynamic behavior of the mechanical system, a mechanical system which can be made up of rigid and flexible bodies. And there are here several examples of. So how do we model these systems? Well, they can be represented mathematically by a system of differential algebraic equations, which are shown here. We have this term which gives the inertia efforts. These are the constraint forces in the system. And here in F, we have several kinds of forces, elastic forces, damping forces, external forces, and so on. So this first equation is the momentum balance of the system. And this momentum balance is supplemented by equations of constraint. In principle, I consider here only bilateral constraints, but we can have many other types of constraints, of course. This system is a nonlinear system of differential algebraic equations. These nonlinearities are mainly here. The constraints can also be eventually nonlinear. And the characteristics are essentially that we have joints, which introduces the kinematic constraints. There are nonlinear algebraic constraints, which are modeled using Lagrange multipliers. And essentially these kind of systems have large displacements and finite rotations, which is known as geometric nonlinearities in the systems. And also eventually we can have a nonlinear constitutive laws which give rise to material nonlinearities. So we have to deal with all these ingredients. The aspect of finite rotations is essential to mechanisms. When modeling mechanisms, we almost always have this aspect which should be taken into account. How do we solve it? For integration, we discretize in time.
And we arrived to systems like this one. When using what we use in our code is the generalized alpha time integration method, in which the discretized momentum balance is expressed this way. The bilateral constraints are there, and they are supplemented with difference equations, which give the relations between discretized velocities, accelerations, and displacements. This algorithm is second order accurate for smooth motion. There are some, the H is the time step, and beta and gamma. These are, and alpha here, alpha M, alpha F. These are parameters which control the behavior of the algorithm. And they are selected normally in this way. They are all expressed in terms of this rho infinite parameter, which is the spectral radius. And this spectral radius controls the dissipation of the algorithm. And I will go back to these parameters afterwards. So if we select these 4 parameters in this way, we can keep the second order accuracy and control the dissipation of the algorithm. This dissipation will play a role when there are numerical oscillations, and for many reasons, these numerical oscillations can be excited, and in this case, the way to control them is to go to very low values, eventually 0 with this parameter. So that's all for the theory of the mechanical part, but since we are dealing with the wind turbine, we have also to solve for the fluid dynamics. And here we have several examples of fluid dynamics problems. In the case of wind turbines, the flow is incompressible with velocities which are in the range from 5 to 25 meters per second. So in this case, for these velocities, the flow can be considered incompressible, and the compressibility appears only at the tip for very high velocities, but still the Mach number is very low. So the assumption of incompressibility of the flow is okay, is admissible. In this case, the equations to solve are what we solve are the incompressible Navier-Stokes equations in the Rand's method. This is a system of differential algebraic equations also, in which we have on one side the momentum balance, the constraint of incompressibility, and in order to model turbulence, these are supplemented with 2 equations in which is known as K epsilon turbulence model, where there are several parameters here which I will not describe. But the system of equations to solve is this system of 3 plus 1 plus 1. We have 5 differential equations together with an equation of constraint which impose the incompressibility. There are, of course, boundary conditions, and this system is in the solver we will use. This system is discretized by using finite volumes method. The solver is what is called segregated, in which the solution is obtained by solving the equations in a sequential manner. It is a very special way of making it. Pressures are computed in a predictor-corrector approach using the simple method. And these time integrations is obtained. The time integration is obtained by a first order backwards Euler implicit integrator. So that's what we have two specialized softwares. So one for flexible multibody dynamics, which is Mecano, and another one for computational fluid dynamics, which is STAR-CCM Plus. So in order to to make the analysis of the wind turbine, we have to make them both interact. And this is what is called cosimulation. In a cosimulation, the different subsystems, the mechanical part and the fluid part, are modeled and simulated separately, but during the simulation, both subsystems exchange that data. So in order to make all these advanced properly, we have to consider aspects. In order to make this cosimulation, we have to consider aspects of implementation, stability of solutions, accuracy, and efficiency. The stability of solutions, the problem is that in order to make them interact, there are some parts which are taken into account in an explicit way. And each time you make an explicit computation, you may have problems of stability. And I will show now. So we have STAR-CCM Plus and Mecano advancing from station Tn to Tn+1. Mecano computes the positions, computes displacement positions, and it gives to STAR-CCM at each time the new position of the blades, for instance, or the new position of the system. STAR-CCM computes the flow, and in return, it will give pressures or forces at the interfaces to Mecano, and this process can be iterated in what we call cosimulation iteration, and up to a given moment where we consider we have conversions. In order to stabilize the mechanical integrator, we since this, you see here, this computation is explicit, you may have problems of instability. And for experience, by experience, we arrived to the conclusion, it is not a demonstration, but by setting rho infinite to 0, it is the spectral radius of integrator, we put it in 0, we stabilize the integration and do not have these stability problems. From the point of view of the integration in STAR-CCM, since it is using a backward Euler integrator, the backward Euler integrator, it is known that the rho infinity is already 0 in that case. So we do not have this kind of problems here. Finally, from the point of view of accuracy, we may play both with the time step of the computation and with the cosimulation iterations. So this is a general view of what we are doing. In the project, we developed a software, several softwares, in order to make both softwares, Mecanos and CEF-Mecano and STAR-CCM, to collaborate. So this cosimulation scheme, we named it SCORE for some CEF STAR-CCM cosimulation running environment. This the aspect of implementation in this case is very important, since we are dealing with systems of a very large number of equations which has to be solved in a parallel computer. So this score, on one side, it is a script for automatic running of cosimulation examples. The score is charged of launching the simulation of Meccano, the running of Meccano, and also the running of star CCM, and set the different data to communicate. This command is finally simply a one-line batch command, which simplifies the way in which the user launches the process. There is the input for this scheme has been made in a JSON format. I will show it here, where we put several data related to communication. There are several configurations options: batch, serial, parallel, pre and post-process tasks, etc. Sometimes there are some codes to be compiled, separate codes to be compiled, which are done directly from score. And we can use, using score, we can monitor and synchronize the two softwares. And finally, since the final objective of the project is to make this simulation interact with the other work packages, this has been implemented in a Docker container, which is a technology which will be used by the other people to make all the pieces of software to communicate. Just a brief look of how it has been implemented. We have on one side Meccano, and on the other side, star CCM. Meccano had already what they call a SAMSEF supervisor, which has been developed to make cosimulation tasks within SAMSEF. SAMSEF is the general name of the software. We developed these two pieces of software here, which are the mechanical interface program and the fluid interface program. The mechanical interface program communicates with the SAMSEF supervisor, and the fluid interface program communicates with the star CCM Plus using the Cosimulation API. Essentially, using all these parts, Meccano sends positions or displacements, which is more or less the same, to star CCM. And star CCM, from star CCM, we get back pressures at the interfaces or eventually forces at the interfaces. This process is controlled using a file, a data file in the JSON format. In order to generate data, we developed a program which is called BNREL. I will show a look, in which we generate in a simplified way the geometry of a wind turbine. It is specialized to generate data for wind turbines. After running of BNREL, we obtain data for Meccano and also a description of the geometry, which is then communicated to star CCM to generate the mesh around the wind turbine. So all the process, all the simulation is started from this single piece of software where we describe the system. This is an example of some tests we have made
For instance, here we have a structure which is composed by 3 elastic plates, which are there. And well, we have a view here of the flow. Okay, well, this test was, this is a view of the output of star CCM. Star CCM is already able to model some elastic parts, so that we were able to simulate this system both by using star CCM only and also in the Cosimulation scheme, and compare solutions and verify that everything was going okay. The description of this system, since we see here there are 3 parts, 3 elastic parts, which should be communicated to both softwares, so that we should tell the Mecano to send the positions of this plate, and of this plate, and star CCM should know that it should goes back pressures over this surface, over this surface, and over this surface. These are 3 separate elastic parts. In the language of the SAMSEF supervisor, this is described in this way. We have here, there are sections in which we say the supervisor communicates the program 1 is Mecano, and the program 2 is the mechanical interface, which is named small mech. And here we are telling that we should send from 1 to 2, that is from Mecano to small mech, the positions for plate 1, and we should go back pressures from the small mech to Mecano on the object which is named plate 1. In some other place we are describing which are the objects plate 1, plate 2, and plate 3. So we see here there are 6 groups of data to communicate from one software to the other. On the score co-simulation data, we have this same information here, and we are telling that plate 1 is the object which is described by the geometry given in the STL file named plate 1. Plate 2 is the object described in the STL file plate 2, and so on. And this data is communicated to star CCM in order to compute pressures that should go back to Mecano. There are some other data here, for instance, the number of coupling of the co-simulation iterations, the time step of the simulation here, and some other data is also given in score. And the format here is what is named as JSON format for the description. So this is just a rough view to make you a view of the complexity of putting 2 softwares running in parallel, which were developed by separate people and separate groups. So then let us go now to the simulation of a wind turbine system. The wind turbine is this structure like this, and we should take into account aspects of wind. There are several mechanisms inside: a pitch mechanism which controls the rotation of the blades, the generator, the control of the system, which is very important. As we show, there are sensors and eventually the cables. It is the output, the power output. So concerning the mechanism itself, we have, as I said, this pitch motion of the blades, the rotational motion of the rotor, There is a mechanism also to control yaw, which we are not modeling now. Actuators to command all these motions. There are external loads, the pressure over the wind, coming from the wind over the blades. There is the interaction of the wind with the tower, and so there is we take into account the interaction of the blades when passing in front of the tower. There are gravity loads, internal loads. We have a torque reaction by the generator, a brake. In some kind of maneuvers, we should take into account the brake. And of course, we have elastic and inertial loads of the different elastic parts. And finally, we have the output power given by the wind turbine. Also, in the simulation, we have to model a controller which reacts to the different wind load conditions and modifies and control the mechanism by modifying pitch, essentially pitch and torque, to achieve the expected output power. And this is made taking into account the particular. In some features of the model, the blades are elastic, and we model them using flexible beams and a deformable skin which is supported over the beams. There's a central hub which has been considered rigid. The nacelle has been considered rigid. The mast is flexible, also modeled by using beams and a deformable skin. And there are particular aspects of the simulation for taking into account the motion. We needed to put a kind of a sliding mesh capability, use a sliding mesh capability in the fluid mesh to follow, in order to follow the blade's rotation, the rotation of the rotor. So this sliding mesh is rotating, and this rotation is coupled with the rotation of the rotor blades. But also, since the blades are deforming, we use also a morphing mesh capability in the fluid mesh to adapt the fluid mesh to the blades deformation. What I will show you some pictures, and this will be made clear afterwards. And finally, this blade rotation, the rotation speed, is being computed as from an equilibrium between the torque produced by the wind pressure and the torque and the resistant torque at the generator. So what we are doing is a kind of bidirectional coupling. There's an equilibrium between what is being computed in the fluid part and in the mechanical part. There are still some limitations. For the moment, the mast has been assumed rigid, and we have the pitch motion is somehow limited. We are working on it. The geometry is being constructed in a separate software, and it is described as STL files. There are 3 STL files for the blade, 1 STL file for the hub, another for the nacelle, and finally another one for the mast. In order to allow the relative motion between parts, and these parts are separated, they are disconnected. For instance, here the hub and the blades are disconnected to allow the pitch motion. We should take into account that in between there is the fluid mesh, so we cannot connect them. Here it's the same. This data has been computed in BNREL. The BNREL, this program is able for now to has been used to simulate 3 different wind turbines, the Siemens 2.3 megawatts and REL 5 megawatts, and we are working on a 15 megawatts model of a wind turbine. It computes, it gives the shape and properties of blades, tower, drivetrain, blade plane, and there are separate axis systems. And it works starting from tables, which are typical for these systems, and where we have the beam structural properties, blade geometry, coefficients. We are not using them, but we have the CLC, the lift, drag, and moment coefficients for the sections, mechanical boundary conditions, and definition of wind, etc. This program is able to generate data for different ways of modeling the fluid. We are working on the CFD model, but we can use also what is known as a blade element method, and also by a vortex method to simulate the fluid. The blades, as I said, are modeled as beams. Here in black, we may see the beam, and supported on this beam by using rigid elements. We describe the profile, the scheme. We give a skin mesh, which is the mesh where the forces and or pressures will be applied coming from the fluid. And so, what else? Well, the shafts in the drivetrain are flexible. We have here, for instance, we see here some rotoids joints. There's an elastic shaft here. There's a joint, a rotoidal joint, the actuator joint here, rotoidal, which controls the pitching. And also there's a controller, which is described by using this program. The beam definition starts from tables like this one, where we have the different structural properties of blade for different section, different radius, and also the geometry is given similarly. We have here a view, another view of how the blade is modeled. We have a flexible beam here, rigid bodies supporting an external mesh, which is only used to translate pressures and forces to the structural beam. The tower is computed, is modeled in the same way. We have, this is a view, another view of the mechanical mesh on different parts, tower, hub, blades. Here's the hub. The blades have been verified, their structural properties by computing the modes when attached to the base. And we verify we are obtaining the correct values, the correct frequencies. So that both the inertia properties and the resistance elastic properties are well represented. The controller has essentially two subsystems. One which controls the generator torque, and the other one which controls the pitch angles of the blades. So in terms of the measure generator speed and the pitch angles, also some values of wind, etc., the controller decides what the generator torque should be and what should be the pitch angle, so as to give the correct value of power. This is a view of the fluid mesh, a general view. Here, all the computation is done inside a box, and the wind turbine is located here. This is the disk which inside this this disk, the disk will be rotating. This is a rotating mesh, which is connected to the box mesh by a sliding mesh interface. And then there are different zones with different refinements, so as to model the different wind characteristics. Here's a view of the sliding mesh. You see all the mesh. I will show you the mesh then, but the mesh is generated starting from the STLs of these parts, which the STLs, the geometry, this geometry was computed in BNREL. This disk, as I said, rotates together with the rotor. And this rotation is imposed by Meccano after verifying equilibrium between generated torque and torque under resistance torque. Here we have different views of the mesh, the fluid mesh. You see this disk rotating with the rotor, the mesh refinement of the boundary. This is in some cases we made this kind of modification of the conical shape so as to allow larger displacement of the blade. We see here how the blade deforms due to the wind pressure. This deformation in large wind turbines can be very large. I will show you computations in which this displacement is in the order of 4 meters or 4 or 5 meters. And so the mesh of the fluid should adapt to the changes in the boundary. In order to launch computations, what about time? Sorry. Okay. Oh, I will move faster. In order to start the computation, first we compute a mechanical solution with a constant rotation velocity in which the blade's deformation under centrifugal forces is obtained. Then we impose the rotation velocity and very progressively apply the wind pressure from 0 to the actual value. And finally, we launch the real fluid structural cosimulation. Why we do this? Because the problem is that the blades are very flexible, and if we impose forces in a certain way, we obtain very large deformations, and the computation stops. We see here the evolution of the main rotor speed. At the beginning, we see a constant rotation speed. And at this moment where we free this rotation, we see that the rotational speed oscillates a little bit and arrives finally to a constant value. I will show you some results by imposing constant wind conditions. Here we model the 5 megawatt NREL wind turbine, which is a wind turbine with a rotor diameter of 126 meters, and the hub height is 90 meters. Here we set a constant wind speed of 12 meters per second, and we see here the main rotor speed. When we look in detail, we see here some ripples, some small oscillations, which are produced by at the moment blades are passing in front of the tower. This is due to the interaction with the tower. The target value is 12.1 revolutions per meter, and our model stabilized almost at 127 instead of 126.7. So the results are we are confident in these results. We see here, we make computations with different fluid mesh sizes, and consider mesh is more or less converged for this purpose. This is a view of the generated power. The generator power, we see here, the power being generated is 5.08, and the target value was 5.1. So it is, again, it is more or less accurate. Of course, this is a thrust of the rotor, the generator torque, and we see these oscillations produced when the blades are passing in front of the tower. The controller has set the pitch angle to 2.8 degrees in order to control the wind turbine in our model. And when we see the target values, the target value was 3.8. So there's just 1 degree of error with respect to these target values. These are views of the flow around the wind turbine, the wind speed. We see the wind speed is constant. This green is 12 meters per second in this case. These are the views of the wind pressure of the blades, the pressure coefficient on different blade sections. We see how the blades deform. This displacement is 4.3 meters. So that the fluid mesh had to accommodate to this motion. If we plot the evolution of the blade oscillations for the 3 blades, we have one blade in red, another blue, another green, and we see with the resulted from several factors. These results from the blade inertia, the inertia of the fluid, also the changes in aerodynamic forces, the excitation of the tower, and other factors. So this is the displacement we are computing at the tip of the blade. Well, this is a view of the flow, straight lines, the vortices. Another view of the vortices generated. And this computation was done in a parallel computer, which is a very old one. And we used 17 nodes for star CCM, 1 node for Meccano. And the computation for these 60 seconds of simulation required 169 hours. That is more or less 7 days. I don't remember. Most of the time, most of the effort is spent in star CCM, in the computation of flow. The score demanded just a bit little effort. This is another simulation in which we imposed variable wind conditions. This computation was done on a Siemens 2.3 megawatts wind turbine, whose rotor is 93 meters. The height is 90 meters also. The time varying conditions were imposed in this way. This is a normalized, the time varying atmospheric boundary layer was imposed at the inlet. And also this velocity profile from the inlet was convected on the domain to generate initial conditions. That is, to generate varying velocities all along the computational box from the beginning, in order to accelerate the computations. If not, we should spend, if we do not do that, we should spend a lot of time in order to make the initial inlet velocity to propagate all along the domain and then see what the results are. Here we see a plot of a turbulent wind around the wind turbine, which is here, and the mean value at the hub height is 9.8 meters per second. So this is a view of the flow. We see now the influence of the turbulence. This is a very high turbulence condition. And we see here the rotor speed, the oscillations, again, the oscillations produced by the blade passing in front of the tower. And the problem we had here in this simulation was that this mean value was very low with respect to the expected power. So the torque and the power decreased, and the model was not able to sustain constant velocity. We see here that the pitch arrived to a 5-degree limit, and then the system lost control. You see, these are the oscillations computed at the tip of the blades. And okay, that's all for this simulation. So, as a conclusion, we developed a platform for retail analysis of large wind turbines. This is a uniform platform to model wind turbines with various flow computation scheme. I did not show it. We are able to use also not only CFD, but also simplified methods of computation of the flow. The CFD is for a detailed modeling. The Cosimulation method showed correct results for CFD and flexible multibody dynamics coupling. And it's important to set a null spectral, zero spectral radius at infinity for stabilization of the flexible multibody dynamics. As a future work, we are working now on the modeling of a 15 megawatts wind turbine. And we are starting to simulate another maneuvers. For instance, we want to simulate the emergency stop of a wind turbine. Okay, thanks all, and the acknowledgement for a project upwards, which supported this work, and CONICET and Nacional, of course. Thank you.
Thank you, Alberto. Very nice, interesting, and detailed presentation. Thank you, Alberto. Some question for the audience?
Can I ask?
Yeah.
Yes.
Okay. Interesting, complex problem, which is also a very, how can I say, very attractive and very on time. I mean, all around the world, the people is looking for wind turbine.
Yeah.
And actually, I did something about that, but I want to know your impression, your opinion, and also your expression on the role and the impact that the gearbox and the gearing mechanism can have on the overall design. I may refer that in my lab, in collaboration with people from, even from Kazakhstan, we developed some gearbox, considering that sometimes the wind is so strong that the power cannot be fully absorbed by the system, and you need to find a way how to waste the exceeding power. So just to say that the gearbox can be, although you mentioned it, but I understood that you didn't give so much weight, but it could be so important. What is your opinion?
Yeah, it's true. We should say that the gearbox is used in wind turbine. The larger gearboxes in industry. It's a very huge problem. When we are talking here of 15 megawatts, it's enormous. We didn't model it in detail in this case, but we are able to do that. And in this case, we simply put a relation of transformation of velocities. We didn't model the gearbox, but there are cases in which we have, not me, but people from some tech has modeled the wind turbine and put a detailed model of the gearbox. And they have noticed, for instance, that there are strange vibration phenomena coupling the wind turbine, the vibrations and in the gears, and the formations in the planetary system is very complex. They take into account this flexibility and so on. So to summarize, it is really a very important factor, and there are a lot of failures. There are several failures or a lot of failures related to failures in gearboxes. It's important to look at them. Yeah, sure. Here the objective was to introduce in the software the capability of connecting to a CFD computation, but of course the gearbox is an aspect to be taken into account. They are working also in another work package. They are working on the fatigue problems on the blades there, which is of course also very important. Composite fatigue in composites. Yeah.
Daniel?
I would like to continue on this issue because Marco took a very, very important point. Because I have contact with some people around here in Brazil that do these. Well, it's kind of niche, it's kind of fashion. Well, it's a mixing of what can the wind turbines can do. Well, they can do a lot, but they have some troubles with the intermittency and so on. But yeah, this gearbox issue is really, really important. And I would like to know if there is, because you mentioned what some people from the engineering say. Well, gearboxes we are trying to avoid because they create troubles, because they have failure and they have this and that. But at this high level, at 15 megawatts, you need to change the behavior. And I would like to know what kind of, what improvement a change of the pace, of the velocity, that the gearbox, the gear ratio, the importance, because we have to have arguments to counterbalance those people that say, do not put any gear there because the gear will fail, and I don't want that trouble for me. I want a counter argument, if you can.
I'm not an expert. What I can tell you is general knowledge. There are two solutions, of course, with and without gearboxes. People I think the people from Pescarmona here and which were also IMSA, were also in Brazil, they work with direct drives. But the problem with direct drives is that the generator is huge. The size of the generator increases a lot. So, but that's all I know. So we have to deal either with the smaller generators and the gearbox, or without the gearbox, but a huge generator which is located at 100 meters height, which imposes several problems as well. And also the electronics is quite complex in that case, I think. But that's all I know. Sorry.
Yes,
I have to exchange a couple of papers with Marco as well, because I have some work on the other side of this issue later. So thank you, Alberto, anyway.
Please, yeah.
Is there any other question? Rogelio, please.
I have a question. In general, I work in the controls area, and when we have a complex systems, we try to simplify the systems, and we design and tune the controller based on the simplified system.
Yeah.
Here I can see that there is an integration of the controller with all the complex systems. Then I would like to know if with your implementation, you can take advantage of the complex controller, and how or where are you implementing the controller? Is a separate package or software, or in the same software that you mentioned?
Yeah, I didn't describe it in detail. What we used here is a simplified controller, which was developed for simulation purposes by people of Samtec. But the software is able to communicate that the controller is connected to the software via a DLL. And what they do usually when working for industry is to give them this DLL connection, and the industry part puts their controllers in connection with the software, because there's a lot of secret in controller design, and they do not want to open it even to a company under the different restrictions and so on. No, they want to keep this knowledge on their own. You see what I mean?
Thank you.
So the software is open to connect with any controller.
Thank you.
Yeah.
Any other question? Yes. There is no question. We will conclude, and I greatly acknowledge to Alberto Cardona for this amazing talk, very complete talk. Thank you, Alberto.
Thank you.
Thank you very much. It's nice to see you, and we are very honored with this presentation at MuSMe. Thank you. Next, we will introduce the static analysis, this kinematic analysis session, sorry. I would like to know if Omar Martin is coming. He didn't respond. So the next presentation will be made by Oscar Castro Campos. Oscar is here.
Hello, Martin. Yes, I'm here.
Hello. Please share your window while I'm introducing you. The paper is an adaptable forward mechanism for data-based model validation from the University, from the UTEC, Peru. Please go on.
Okay. Good morning, everyone. Today, I'm Oscar Castro. I'm mechatronic engineer. I studied mechatronics engineering at UTEC. And today, I'm going to present the work done in collaboration with Axel Céspedes and our advisor, Elvis Jara. The work is titled An Adaptable Forward Mechanism for Database Model Validation. So, this is the main topics that I'm going to talk about. The first one, motivation. So the forward mechanism has been one of the most studied in the last decades. So this is because its simplicity and practicality for design. This mechanism is widely used daily. For example, a windshield, a pair of locking pliers, or an oil well pump. And multiple forward mechanisms can also be used as a basis to form more structured mechanisms, such as the Theo-Jason mechanism, which has two forward linkage and has proven to be quite efficient in generating smooth work. So, in this presentation, we are interested in studying a new method to get a more reliable model and close to reality. So for this reason, we decided to use a database method instead of just the kinematic and kinetic equations. Because there are many factors why the analytical position differs from the real position of the forward, or the forward mechanism or another one. So it may be due to the sum of system disturbances, because the connections between the links are not perfect, or because there is a response time or fatigue in the system. So first, I'm going to explain about the prototype that we built to prove this, to validate this method. So this is our adaptable forward prototype. The structure of this mechanism was made by laser cap using 5 millimeters of MDF. The part of the mechanism was made with a letter A, B, C, D, and P, which are crank, coupler, rocker, ground, and coupler station, respectively. So in this prototype has two actuators. One stepper motor is used to control the angular position of the crank. One linear actuator for the crank replace the crank. So here we have the detectable mechanism. And the both motors are controlled using an Arduino Uno. And with this microcontroller, we get the data. About the dimensions, the crank, that is the linear actuator, varies between two extreme positions. The minimum is 13 centimeters, and the maximum is 15.8 centimeters. The length in centimeters of each part, coupler, rocker, ground, and coupler extension, are 20, 17, 22, and 16 respectively. And the dimensions of the links satisfy the Grashof conditions in each variation of the crank. We take this consideration. So, the method that we use in this paper is the position analysis. The method that we use in this paper is the computationally efficient solution position, such as in E constant. There are different methods that we use this one. And we didn't discuss about the velocity acceleration, both velocity and acceleration analysis in this paper, but could be obtained simply by applying finite difference to the position analysis. So in this image, we can see the variation of, in the first one, we can see the trajectory of P for the crank extreme position. And in the second one, we can see the trajectory of P for a sinusoidal variation of the crank. That we will use the second variation to simulate and validate our method. So the data sampling process. We have two inputs, C1K and C2K, and one output vector, RK, that are used for this process, where 300 samples were experimentally obtained. So the input is basically the crank. C1K is the crank angular position, and C2K is the linear actuator's PWM signal. And the position of the point P, RK, is the output of the vector. So some considerations that we take here is that the data sampling experiment must cover the entire operating domain of the system. Here I'm talking about the linear actuator. the minimal and the maximal extension. And in addition to being persistently excited in order to have a good database modeling. And the data set is, well, is used as a real reference for the database estimation process that I'm going to explain in one moment. So the non-temporal prediction method, well, this method is based on the recursive least square algorithm. Well, these are the equations of the real square recursive least square algorithm, where gk is the correction gain, yk is the data output, and alpha is the forgetting factor. But in the non-temporal prediction method, the current predicted parameter vector theta and the covariance error matrix are described in this expression. So our application. If you want to know more about the non-temporal method, you can check our first reference that I'm going to show you later. So the application, so our forward linkage, we can consider it as a black box system. So now nothing is now about the physical equations that define the trajectory of the point P. So thus only the input and output data is available to model this system. Our first candidate model was a finite impulse response, the FIR filter. But the non-stationary of this model is reached by considering type varying parameters. So the estimated FIR model with the time varying parameters is expressed in the seventh equation. And the electable forward linkage is not a non-linear system, so the linear FIR filter is not an appropriate candidate to model it. So we use another instead of this one. So from a causal point of view, it's important to note that the first degree of freedom of the system is defined by the Crank angle, and the second one is defined by the PWM signal. So notice the current vector positions depends on its position, and error is so the previous position. So this makes sense in this type of system. So under this generic and basic consideration, the non-temporal regression model is proposed by the following equation, is the F equation, where the components of vector are the following, the 9 and 10. So the model is a linear in the regressor, and the parameters are the unknown functions. So AK and BK are just the coefficients of the model. So we estimate these coefficients to model the system. In this picture, we can see the estimation of the position in x-axis and y-axis over time instant k for estimation process using the non-temporal regression methods. That is the black line. The recursive least square filter is the dashed gray line. So we can see that the non-temporal regression method has a fast convergence and achieve good traceability compared with the errorless-based filter. And this cannot trace the variation of the model output. So for To see the trajectory, we made this graphic, and we have to test the robustness of this method. We add noise to test the input data, and we compare the model output and the actual output for two scenarios. The first one with Gaussian noise with variance equal to 1, and the second one with variance equal to 10. So as was expected, the test error is greater than the estimation error. We can see this in the following table. Furthermore, the error increases the more noise is added to the input in the estimation process. So, in conclusion, a detectable forward prototype was proposed in this paper in order to validate the non-temporal regression method. The method proposed is more accurate compared to the analytical one because it considers the noise of the linear actuator. And it's a better option in case you want to design a position control to the mechanism and get new desired gate patterns. These are the reference that we use, and thank you so much.
Thank you, Oscar. Thank you for your presentation. Is there any question for Oscar? So I have a question. This model-based methodology was used by other researchers in mechanism design?
Specifically in mechanisms, no, but well, in mechanisms, no is the first update because the proposed methods was published in 2020. So we use the recently method.
Okay, maybe it's not justified because they are closed form equation for mechanisms, but it will be applied to very complex linkage.
Yes,
Marco has a question.
Yes, a practical question. Whatever it could be beautiful from mechanical point of view, from formulation point of view, we needed to look at the practical advantage. What do you propose the advantage on the existing formulation? I mean, your computation is faster, more accurate. How much faster can be, even for a typical industrial robots? Because if the improvement is not significant, it will not be considered of interest.
Okay, for as Martin says, we can use this method to more complex systems, but also we can use it to consider the noise of a system. So, for example, in robotics, we use calibration methods to know what is the output of joints, or maybe some linkage are. The dimensions of some linkage are not exactly as the dimension that we propose. So in this case, we can use this method. And we don't use a lot of sensors. We just take the data about the position of the N effector and just the two inputs that are practically voltage. We don't know nothing at all about the physical model.
Thank you. Elvis, just a comment from Elvis.
Yes, I would like to do a comment. Actually, I was working with Oscar as well. And it's good, the question of Marco. I would like to say that some advantage of the method is that it is a statistically efficient method compared with other ones like the machine learning based methods, for example.
that need more iteration. This method is a real-time estimator. Then we use this method for other kind of process, for other kind of problem, and then we try to use it in an mechanism modeling problem. We try to experiment how does the proposal work with this kind of problem. Maybe the practical advantage of this method is the real-time characteristic. Maybe we can use it when the mechanism change fastly. Something maybe high noises, I don't know. Yeah, we just try to test the method with an real linkage. Then Oscar implement this prototype based on a linear actuator, and we add some noises, and we tried to see if the proposal works in this scenario.
Okay, thank you, Elvis.
Mm-hmm. You're welcome.
Nice project. So next presentation is from Marco Antonio Garcia. It is called, the title of the work is Kinematics of a Robotic System for Rehabilitation of Lower Members in Hypotonic Infants. Marco is here. He confirmed recently.
Yes.
Please share your screen.
Yeah.
Is Esther Lugo here also?
No.
Okay.
Okay. Kinematics of a robotic system for rehabilitation of lower members in hypotonic infants. My name is Marco Antonio Garcia. Collaboration is la doctora Esther Lugo González, doctor Manuel Díaz Montiel y el doctor Ricardo Tapia Herrera. Introduction. Hypotonia is a condition characterized by the deficiency of muscle tone, which mainly occurs in infants. Palliative treatment is passive therapy, and to the best of the author's knowledge, there are no robotic devices for infants with this pathology, as dimension, weight, materials, or mobility values must be very specific. The basic passive therapy applied to the lower limbs in hypotonic infant focus of the hip, ankle, and knee movements generated of the sagittal plane. For this condition, parallel robots have been used to generate movements and specific trajectories in this type of rehabilitation. Robot propulsion. In this case, 5-bar mechanism is the basic of robot. Kinematic analysis and simulation that generate flexion, extension, movements, and the hip and ankle and knee. And this robot to achieve of the infant's rehabilitation phases presented. The 5-bar mechanism has 2 degrees of freedom, which generate 2 independent movements for carrying out a previously established trajectory, flexor extension movement. The infant's characteristic 500 millimeters of length provides the dimension of the OB and D links, meant that the links for B, if G, JH, and HO can be calculated. For restriction and calculation purposes, the dimension of the OB and BA links are fixes, but can be adapted to the infant's development. The calculated 5-bar mechanics trajectory synthesis considered figure 2 and the equation 1-2. Equation 1, write the complex number, write and using the Euler formula complex number. A kinematic for 5-bar mechanics. For inverse kinematics, the coordinates of trajectory point F and Pxy are known and the input angles of the manipulator modes be calculated. The output point Pxy in reference frame of xy. Question 8, 9. Be knowing the position output point Pxy, inputs to reach this point can be obtained theta 2 and theta 5. Implementation in 5-bar mechanics are two trajectories, circumference and the equation 14 and ellipsis equation 15, and the figure circular an elliptical path. Okay. Results and discussion. With the point F position at each instant of time and the use of polyfit to polynomials are constructed which describe the behavior of the angles theta 2 and theta 5. I show equation 16 and 17. The polynomials are input on the angles theta 2 and theta 5. And the actuators in Adam's view is theta 2, constructor polyfit, and theta 5. The polynomials constructed in MATLAB are an introduction in the theta 2 and theta 5 in the model Adams to generate movement in the mechanics. The angular displacement is also measured and compared with the result obtained on the mathematical model. Mathematical model is theta 5 and theta 2 trajectory, and polynomial and theta 2 and theta 5 polynomial. Okay, and the view 4 show the graphs of the mathematical model MATLAB polynomials when comparing with the results of the model in Adam's view. There be the mechanism. The result obtained of trajectory for point Pxy in the figure 2 corresponding to the proposed trajectory and the similar results were observed in figure 5, obtained with a MATLAB software and Adam's view, compare Pxpy and the MATLAB Adam's view. To perform the velocity analysis in equation H and 9 were derived with the range of the temp and simplified has this equation. Write equation 19 and 18 in matrix form, equation 20 and 21. We are escriben matricial form. Equation. Okay. For the velocity simulation, a circumference trajectory was used and the test was performed with 10 millimeters per second with the results on the figure 6. Can be seen the velocity omega 2. Right. Actual start in the 0.4 seconds and increasing in the time progress in the reach 0.0 that takes per second after 118 seconds. For the case in actuator 2 is initial velocity is 0.34 dex per second, the not B and the omega 5 and the crescent in the race and 0 that 14 seconds for dex per seconds. Over a period on 118 dex per second, when this angular velocity is actuator the 10 millimeters per second at the point F in the mechanism is achieved. Okay, final result, the simulation mechanics in Adam's view is shown the flexion position and the lower in the sagittal plane can be observed. The symmetry in infants' lower limbs compared with the mechanism position is also observed. Conclusion. A mechanism is presented in the used to the design for children with hypotonia rehabilitation prototype, and it was observed that is necessary for the mechanisms to follow the pre-established trajectories in rehabilitation session. In this work, the following of a circular trajectory and ellipse wise respected to show that the designated mechanisms can follow a specific movement such as flexion extension generated with the hip, knee, and ankle in the sagittal plane. And the rehabilitation devices is made of a 5-link parallel robot divided in 3 parts, 2 with 4 bars and the 1 5 with this last bar in focus of this study. For inverse kinematic calculation, the constraint equation were considered for obtain the behavior in position and velocity. The graphical results were validated with the mathematical model in MATLAB, which has similar behavior in the model in Adam's view compared to velocity and position. Thank you.
Thank you very much, Marco. Is there any question for Marco? No. Okay, since we are shifted on time, we will do a break. Thank you, Marco, very much. Sorry. Nice work, and tell Esther Lugo also that this work was amazing. Go on keeping on trying to improve it and enlarge it with better results. So and we will do a break now until 12 p.m. Next presentation after the break will be made by Leonardo Rincon. Iracosi Viven will be replaced, will be given by Marco Zuccarelli. And then Federico Cavolilli will start the dynamic analysis session. Thank you all thank you very much to all the audience.
Just a comment, Martin. Sorry, the next session will start at 11:45 according to the program.
Yes, Leonardo.
Right?
Will be shifted. Will be shifted.
Thank you
and
very
you
much.
will start at 12 o'clock.
Okay. Thank you very much.
Okay. No, thank you. So we will do a break now. Thank you.